Good afternoon, everyone. My name is Baran. I'm a PhD student in EPFL. Today I will talk about magnetic resonance imaging scan designs that are learned directly from data. Magnetic resonance imaging, my colleagues were also talking about them. It's a quite important imaging modality. It has the advantage of not having radiation, and but the disadvantage is that it is slow. In some applications, for example, it can take up to an hour, and that's why it is important to be able to speed up the magnetic resonance imaging scans. For example, if we can speed up, that means we can use better the hospital infrastructures. We can scan more patients in the same amount of time. That's also comfortable for patients as well. For example, if I can just spend 5 minutes in the MRI machine instead of 1 hour, that's also good for me. And for certain cases, it's not easy. For example, children, they need to be sedated. They are given drugs. They sleep during the scan. Or patients with respiration problems, they have to hold their breaths so that the image doesn't move, which is not easy for them. So if you can make these scans faster, then it is good for many reasons. Now let's make a quick overview of magnetic resonance imaging. As some of you already know, what an MRI machine sees is not an image itself, but it's a Fourier transform. It's 2D Fourier transform of the image. And in the setting that we use, slice by slice acquisition, the machine takes line by line this Fourier in these Fourier pixels, and if the machine measures all of them, you can get a nice picture. For example, it's here a half picture. But the thing is, if you take all of them, all of the lines here, it will take some time. And one way to reduce the time is take just some lines, record the Fourier transform only on these lines, which will be faster. But if you take the inverse Fourier transform to go back to the image domain, then you see a lot of artifacts. But there are algorithms today, there are reconstruction algorithms that are able to obtain good image reconstruction from these undersampled measurements. They are, for example, called compressed sensing algorithms. But our focus in this work is not proposing new reconstruction algorithms, but the question that we focus on is which set of lines, which set of samples I should choose in order to get a good performance. So I was telling that there are algorithms that are able to reconstruct. The basic model is a linear model. The X is the signal that we want to recover. And A is, for example, in the case of MRI, it's a Fourier transform, a sub-Fourier matrix. And this reduces the size of the image. And then from a small number of measurements, the algorithms are able to reconstruct the X with a certain quality. And how do they do it? They use some assumptions. For example, the images, as you already know, they have certain structures. They are sparse in wavelet domain. That means in wavelet domain, the coefficients there are only a few strong coefficients. Or there are flat regions which can be exploited as well. There are algorithms, for example, total variation, minimization, basis pursuit, etc. And the theory of compressed sensing, it says that we should try to design the subsampling in a way that minimizes a property called coherence. I will not go into detail, but basically it is how similar the measurement and sparse bases are to each other. In this context, for example, there's a similarity between the Fourier and wavelet domains. And in practice, some typical approaches to design a subsampling, to choose those lines, for example, those are based on some models, some probabilistic models. For example, a very well-known method, it's called variable density sampling. It uses probability distribution functions that favors these lower frequencies in the middle because there are more information there, and also randomly selects some higher frequency lines as well. This is one method. Other methods, for example, they can use some reference images to obtain this probability distribution function, or one can simply do a parameter sweep to try many probability distribution functions and choose the masks that give the best performance. But in all of these cases, there is a probabilistic model, and what we propose is that we will not base our approach to a specific model. We will directly learn the mask, the sampling from data. And we call this learning-based compressive MRI. And how do we do that? We have a certain amount of training data. And we start, here you can see in this video, we start with the empty set. And at each iteration of our algorithm, we add the line that increases the best reconstruction performance to our sampling mask. And then we keep doing this until we reach a desired subsampling rate. Of course, this is computationally very heavy, because at each iteration you have to try many candidate lines. And these reconstruction algorithms you need to reconstruct, and these also take time. But the good thing is this can be parallelized when we use a computation cluster. Then this can be, for example, typically done in a few hours, depending on the reconstruction algorithm that we use. Now I will give you some comparisons. First, I will give in a setting of a single coil MRI, which means basically that at one scan, I just record one image. And before I give the results, I need to also define what PSNR is. PSNR is a metric in image processing that defines the image quality, peak to signal noise ratio. It is given in log scale decibel. And in this plot, I compare, for example, our approach, learning-based scans performance, with the two model-based approaches, the red one and the blue one. And as you can see, with different subsampling rates, for example, at 0.2 subsampling rate, which means 5 times faster scan. But with respect to different subsampling rates, our method consistently gives a good image quality. And here also you can see in this table, with different masks and with different reconstruction algorithms, our greedy learning-based method gives superior performance than the model-based methods. We did this for different reconstruction algorithms, as you see. Total variation is a very well-known algorithm. Basis pursuit, BM3D is originally denoising, but it's also recently used for image reconstruction. We even trained a neural network to use a recently popular neural network approach. And for all of them, consistently, we get superior performance. And just to see some visual quality, I put here some image reconstructions. On the columns, you see 2 different reconstruction algorithms, basis pursuit and neural network. And the rows, the first 2 rows, are the model-based masks. And the last 2 rows are masks and reconstructions with our greedy learning-based approach. And here, you can immediately see actually that in terms of image quality, there are many artifacts in this model-based mask, but the masks that are learned directly from data, they don't have these artifacts. And here, there's another image quality metrics. It's called structural similarity index, which is also popular because it's a better approximation of human perceptual system. In terms of those SSAM and PSNR, we also get better performance. Now I move to another setting, multi-coil MRI. In multi-coil MRI, which is more practical, it's used widely in the hospitals. In one acquisition, at the same time, I record multiple copies of the image. I have, for example, for the brain MRI, I have, for example, in this case, 4 coils, and each of them records an image. For example, this coil is close to that part of the brain. That's why it has a brighter, it has a higher sensitivity to this part. And the advantage is that when just like in the multi-antenna systems in the communications, when I have multiple images, when I combine them, we can get better image quality. And there are algorithms, recent algorithms, that combines the advantage of multi-coil imaging with ideas of compressed sensing. And in the experiments that I'm going to show you, we trained our masks specifically for this kind of reconstruction algorithms. 2 main approaches. One of them is sense. It exploits the sparsity of image after estimating these sensitivities. And another approach is Aloha. It transforms the image reconstruction problem into a low-rank completion problem. And now let's, oh, what happened? Here. Now let's see the performance comparison in this multi-coil setting. The blue ones are learning-based greedy methods. And the red one is a model-based parameter sweep. The black one is also another model-based method, and we also plotted the performance of just taking the middle part, the low-pass mask. And we see again consistently that this greedily designed learning-based mask give better performance for both of the reconstruction algorithms, Sense and Aloha. And here in this table, we check the performances for a fixed rate, 20%. And there are important things to notice here. For example, on the rows, you see the masks that are optimized for different subsampling, different reconstruction algorithms. TV and basis pursuit are for single coil, Sense and Aloha for multi-coil. And on the columns are different reconstruction algorithms. And what we see, for example, if we take the example of Sense, we see that one really needs to use a mask specifically optimized for this kind of reconstruction to get a good performance. This is average over 100 test slices. And if we don't, for example, if we use single coil masks with this algorithm, we have a performance loss. And our method is able to specifically optimize the masks for a given reconstruction algorithm. And now let's see the visual quality in this setting. Here we see that actually our masks that are optimized for the multi-coil setting, they are much more widespread and evenly distributed compared to optimal single coil masks. And in these 4 images, we use just one multi-coil reconstruction algorithm, Aloha. And we compare 4 masks. This is a single coil optimized mask. This is a model-based mask. This is another model-based mask. And this is our optimized mask for multi-coil reconstruction. And again, you see these other methods, they have artifacts, aliasing artifacts. But in the case of using an optimal mask for this specific setting, we don't see those artifacts. And we also moved to dynamic MRI setting. Here, the challenge for us is that there are too many data to handle, and the grid algorithm take a lot of time. The dynamic MRI is just a sequence of images, for example, for heart, for vocal tract, so in order to overcome this challenge of processing big amount of data, because the reconstruction algorithms are also slow for this setting, what we did is we use a stochastic grid algorithm, which means that at each iteration of my algorithm, instead of testing all possible candidates, I can stochastically choose a random batch of candidates, and then I pick the best candidate out of them. And this gives a lot of speed up. For example, here you see greedy versus stochastic greedy for different reconstruction algorithms. These are state-of-the-art reconstruction algorithms for dynamic MRI. For this experiment, we use different number of cores in the computational cluster. That's why when we adjust for that difference, we see around 60 times speed up, which makes this thing practical. For example, in 1 day, in 5 hours, one can optimize the mask for this setup. And one can ask whether we lose something when we speed up the algorithm. It turns out that we don't lose much. Stochastic and greedy, they give a very close performance. In cyclicis, some sampling rates, stochastic gives even a better performance, and it's still better than a model-based method. Here you see the reconstruction quality. For vocal tract MRI, dynamic MRI images. The first column is at 10% subsampling rate. The first row is coherence-based, it's a model-based method. And the second one is a learning-based method that we learned with the stochastic greedy. And the masks are also dynamic in this case. They can be different with respect to time. And the mask that we learn, it's able to adapt this setting, and you see there are a lot of artifacts again with the model-based sampling. And these masks, they are not visible. These artifacts, they are not visible. And if you even go to 20% subsampling, 5 times iteration, our mask able to produce a reconstruction that's almost indistinguishable from a ground truth. And you see this behavior is again consistent with respect to different subsampling rate. Now I will conclude my talk. So we provide a data-driven approach to design subsampling for different MRI settings and reconstruction algorithms. And this largely eliminates the artifacts visible in the model-based methods. This is important because in order to make these faster reconstruction algorithms being used in the hospitals, one needs to really rely on the reconstruction performance and high quality. And we believe that our method is an important step towards the adaptation of these fast algorithms in the hospitals. And we also show that it adapts to different settings and different reconstruction algorithms. Our framework is quite general. Some future directions. Well, if it work for dynamic and multi-coil, this can maybe also work for different MRI settings, diffusion MRI, 3D MRI. And it can also work another, for the biomedical imaging modality, for example, computed tomography. Maybe we can use this approach to decrease the amount of radiation that's present in this method, for example. And also it would be good to jointly optimize the sampling, reconstruction, and image segmentation with this framework, for example, using neural networks that are becoming more and more popular. With this, I would like to thank you for your attention. And if you have questions, I will be happy to answer.
Thanks a lot, Baran, for your talk. Who wants to start with the first question to Baran? Everything perfectly clear. Are we getting close to coffee break?
Do you think this could also be applied to trajectories that do not acquire along lines, like radial trajectories?
Yes. For example, we had done some preliminary work, for example, in the case of 3D MRI, where you don't have to choose line by line, we can choose pixels. We have shown some improvements. We need to work more on that. But in theory, yes, it can be applied. It can be also applied to radial acquisition, where you sample different lines. Yeah, more research is needed to understand those cases, but in theory, yes.
And about the stochastic approach, do you sample uniformly the mini batches, or do you?
Yes, it is totally uniform. Among all candidates, we choose uniformly a set of batch, and then we pick the best in this batch.
Because you know that good candidates, probably you'll want to sample more from the center of the K-space.
Yeah, that's true. But if your batch is not very small, if it is big enough, then with high probability you will also be trying a candidate near the low frequencies. So that wasn't a problem.
Thank you.
You're welcome.
Great talk. Question about the sampling rate. Do you think it could be online modulated adaptively according to the sample? Like interesting parts sampled at a higher rate with respect to the areas that are not so interesting?
That's a very good question. For this to be practical, the reconstruction algorithms also need to be online. They should be, if we can do reconstructions at the same time as acquisition, then one can check the quality online, and then once we get enough quality, we can stop, or when we see that in some part of the image the quality is not good, one can adjust the rest of the acquisition to this. But as I said, I think it would be important to be able to use very fast reconstruction algorithms. For example, neural network, they are a good candidate for this. It takes a lot of time to train them, but they are very fast. They can provide very fast image reconstruction.
By fast, you mean
like, for example, 0.01 second. You can use GPUs, and you can even make it much faster.
Are these algorithms already implemented in commercial systems?
This algorithm, that's a good question. Siemens and Philips, they are doing research. I have seen some papers from these researchers, their research units. It is starting now. It's very new, but it is starting now. And I also observed that they are more conservative in the sense that they were not advertising, for example, 20% of subsampling rate, but they're advertising 40%, which is also good to make it more reliable. But so in a few years, we can see this kind of reconstruction algorithms being used in the hospitals.
Thanks, Baran.
Thank you,
Baran. And thanks to the three speakers of this session. Again, very interesting session. We bought ourselves 30 minutes of coffee break. You're all welcome to share coffee in the